This is section 2.1, Basics of Functions, part 1. So this slide right here just shows the inputs of the apple in that function h box, and then it shows that the outputs are the apple sliced up. So it's just giving an example of the input and the output of functions. Whatever you're plugging in for x or x itself, that will be the input, right? And then when you plug x into that equation, whatever it calculates to, that will be the output. And so that's what that second line is showing you. Here it just explains to us that when we see the f parentheses open, x parentheses closed, that we read that as f of x. And so we read that entire equation as f of x equals x squared. F is not a variable, so that doesn't mean like some value represented by f times the value represented by x. It simply is just expressing that f of x function. So we have the definition of a function. They always have funky definitions that are just tend to be more confusing. It says a function is a correspondence from a first set called the domain to a second set called the range, such that each element in the domain corresponds to exactly one element in the range. So that just sounds like a whole lot of information. In other words, every x value in a function has exactly one y value. So we've seen a table of values, right, where for every ordered pair, there's an x and a y value. Well, with a function, every x value has exactly one y value. So it cannot have multiple y values. You won't see like 2, 5 as an ordered pair and 2, 6 as an ordered pair, because that x of 2 now has 2 y values. We'll see that better in this next slide. So in this first example, we see that every x, 1, 2, and 3, has exactly one y, right? The first ordered pair is 1a, second ordered pair 2b, third ordered pair 3c. So that's just that each x grouped with one y. So that would be a function. And then in the second, I'll reiterate the check. In the second example in the top right, again, we see every single x has one y value. So 1 is paired with b, 2 is paired with c, and 3 is paired with a. So that would be a function as well. In this bottom left example, 1 is paired with a, 2 is also paired with a, and 3 is paired with c. This would still be a function though, because 1 only has a single y, and 2, the x of 2, only has a single y. Even though they're the same y's, we're looking at the x's, right? So it still has a single y. And then 3 has a single y. So that would still be a function. But in this bottom right-hand corner, we don't have a function because look, 1, the x of 1 has a as a y, and it also has b as a y. So the ordered pairs there would be 1a and also 1b. So the moment we have that occur, it is not a function. This slide is asking us to determine whether the following relation represents a function. So the ordered pairs that are given are -7, 4, 8, -3, 3, 3, and -3, 3. So remember, if it represents a function, then we're making sure that every x only has one y. And it's actually already graphed right here. We have -7, 4. Okay, so for that -7, when we traveled back to -7, we know it only had one output, one y, because we only see one point there, right? We only see one ordered pair there. If there was another one here, then we'd be like, oh, hold on. There was another -7 and then a different number as a point. So we know that that one's good. And then we have 8, -3, okay? Then we have 3, 3, and then -3, -3. So I see that every single x has one output, one y. So does it represent a function? It does. Okay, and then it says, well, what is the domain? Remember that the domain is every single x value, right? So we can give an exhausted list right here because we only have 4 ordered pairs. Now, you'll see later on that when we have like a whole graph that we're considering, then we're going to have to use interval notation. But here, we can go ahead and list them all because we only have 4 ordered pairs. So the exhaustive list of this would be, remember we said domain is all the x's, right? So we have -7, 8, 3, and -3. And that would be this last choice. Okay, now they want a list of what the range is, right? And again, we're going to give this as an exhaustive list because we only have 4 ordered pairs. So it's quite simple to just list all 4 of them, right? We have 4, -3, 3, and -3 again. Now -3 repeats itself, so because of that, we can only, or we only need to mention it once, right? So we have 4, -3, and 3, which would be the last choice. All right, it says to use the vertical line test to determine whether the given graph is the graph of a function. So we saw in that last example that when we graph those ordered pairs, actually, let's go back to it. When we graph this ordered pair, these ordered pairs, I can take a vertical line, right? So let's say that I took this line, and if I was to drag it across this graph, at every single point, when I pass an ordered pair, there's only 1 point touching my line, right? So I keep going. When I got here, 1 point touching my line. Again, kept going. Right here, 1 point touching my line. This is called the vertical line test. At any time, if I was to take a vertical line across my graph and there was more than 1 point, then I would know that it was not a function because that means that my x had more than one y. So let's take a look down here. Okay, so if I was to take this vertical line and drag it across at every single, and you know, I'm not doing all the lines in between, drawing all those lines in between, but at every single point in the graph, at every single part in the graph, only 1 point is touching my vertical line. So this would be a function. Okay, so same question. It wants us to use the vertical line test to determine whether the given graph is the graph of a function. So if I took this vertical line and I started to drag it across, look, immediately when I got here, I'm touching 2 points, 2 ordered pairs. So I know at -5 that I have 2 outputs. And then same thing at -4, I have 2 outputs, and then all those points in between, all those x coordinates in between. So this would not be a function. Okay, same thing. They want us to use that vertical line test. This could be a little bit tricky because sometimes we'll want to say no at first glance. But look, if I was to drag that vertical line across, so now it's here, here, you know, and all the places in between. At no point am I touching more than 1 point, right? Right here, I'm here. Right here, I'm here. Right here, I'm here. So as my vertical line travels from left to right and crosses my graph, it is always only touching 1 point on the graph. Therefore, it passes the vertical line test and it is a function. Okay, they want us to determine whether the following equations define y as a function of x. So it's asking us, are they functions? Okay, well, this right here from some of the previous lessons, we know that this would be a linear function with a positive slope starting at 0, 1. So looking something of this sort. Starting at 0, 1, and then it's traveling up 2 over 1, up 2 over 1. So my line is not those staircase lines. That was just my travel. My line would be somewhat similar to this on this graph. So yes, this would be a function. Okay. Y equals 5, again, from previous lessons, we know that that is a horizontal line. Let me use a different color so we can see this a little bit better. And that would look something like this. And so if I was to take a vertical line across my graph from left to right, at all times, it would only pass through one point. So yes, it is a function. And then on this one right here, x equals -3, again, from previous lessons, we know that that line would look something like this for that graph. So now, if I was to pass a vertical line across my rectangular coordinate system from left to right, when I would get to x equals -3, I would not only be on more than one point, I would be on all the points of that graph. So this would not be a function. The moment that it is on more than one ordered pair, as it travels from left to right, that vertical line, then it's not a function. And so that one is definitely not a function because it's actually on the entire graph. Okay? They say determine whether the following equation defines y as a function of x. So remember that our definition of a function, our simplified definition of a function, is that every single x has only one y value, right? So let's go ahead and choose an x and plug it in and see if only one y comes out. So we're going to choose 11 for our x. And let's solve for y. So 11 minus 2 is 9. 9 equals y squared. We're going to do the square root of y squared so that it's just y. And then we'll do the square root of 9. The square root of 9 is positive or -3 because positive 3 squared is 9, but -3 squared is also 9. So that means when x is 11, y can be positive 3 or y can be -3. So that right there shows us that this is not a function because the one input of x equals 11 is giving us two outputs. It's giving us two y's. So no, it's not a function. Okay, they want us to evaluate the function f of x equals x squared plus 6x plus 4 at the given values of the independent variable and simplify. That's a very wordy way of saying plug and chug. So they're giving us a function and we see that x is the input. And then in questions A, B, and C, they're showing us what they want us to check as the input. So I'm going to write the function down here. F of x equals x squared plus 6x plus 4. And then they give us 2 as the input for part A. So every place that I see an x, I would just plug in a 2. Oops. And then I calculate that out. So 2 squared is 4, plus 6 times 2 is 12. So 4 plus 12 is 16, plus 4 equals 20. So basically when x is 2, y is 20. When I have an input of 2, I have an output of 20. Okay, for part B, let's choose a different color here. They want me to have x plus 3 as my input. So again, every single place that I had x, I'm going to put x plus 3. So x plus 3 squared plus 6 times x plus 3 plus 4. Here I'm going to FOIL So just like if I had 5 squared here, it'd be 5 times 5. I'm going to do x plus 3 times x plus 3. Let's simplify that. So I distribute. To each of those terms, I get x squared plus 3x. And I take this second term and distribute it to each term. So plus 3x plus 9. Then we'll simplify it down here. X squared. I combine like terms to get 6x in the middle there. Plus 9. And that was just my x plus 3 squared. So now I'm distributing this and drop it down. Plus 6x plus 18 plus 4. Lots of room for error, so be careful there. Okay, I'm going to combine like terms. So I have some x terms there. I have some constants there. F of x plus 3 equals x squared plus 12x plus 31. Okay, we still have part C. We'll go ahead and do this on this. I'll box it out here. Okay, so again, this is part C. They want me to plug in negative x for my x. So every single place that I have an x in the original function, I'm going to put negative x. Okay. Negative x times negative x would be positive x squared. If you did not put that negative x in parentheses, you can end up leaving it as just negative x squared. So be careful of that. I definitely would make sure that when you're plugging values in for your x in a function that you put it in parentheses. It's just a good habit to have, especially when you have these negatives. Okay, positive 6 times negative x is negative 6x, and then plus 4. Let me write that a little bit neater. Well, there we go. X squared minus 6x plus 4. So notice that when we had an input, that's a constant, so there's no variables involved, our output ends up just being a constant, right? We had an input of 2, we had an output of 20. But when we had a variable still involved when we did the input, so instead of, we put x plus 3, right? That has a variable, has x in the mix. Our output also had a variable in it, x squared plus 12x plus 31. And then same thing when our input was negative x, our output was x squared minus 6x plus 4. So that might be a way for you to check, like, okay, if I had a variable for my input, why do I just have a constant for my output? All right, they want us to evaluate the function at the given values of the independent variable and simplify. So again, we're just doing plug and check. We're going to plug it in and calculate it out. So f of negative 1 would be 3 times negative 1 squared minus 1 over negative 1 squared. Calculate that out. I end up getting 3 times positive 1 minus 1 over 1. 3 times 1 is 3, so 3 minus 1, I'll go ahead and write it, over 1, and then I get 2 over 1, which is just 2. Now, if I have a constant as an output, then I cannot have had a variable in my input. And when I check, I'm like, yeah, that makes sense because I just had negative 1, which is a constant. All right, f of 2, 3 times 2 squared, so plugging into every place that I have an x, over 2 squared. 3 times 4 minus 1 over 4. 12 minus 1 over 4, 11 fourths.